Picture this: you're floating in the deepest, darkest expanse of space, far beyond our solar system, far from the familiar glow of stars we know by name. All around you are vast, swirling clouds of cosmic dust and ionized gas, glowing with strange colors, hiding secrets older than our sun. These aren't just pretty pictures. They're the nurseries of new stars, the graveyards of old ones, and the silent witnesses to events we're only beginning to understand. But what if I told you these clouds aren't entirely silent, that some of them are whispering or sometimes shouting in a language we're desperately trying to decode? For decades, astronomers have tuned their massive radio telescopes toward these interstellar gas clouds, expecting to hear the predictable hum of cosmic chemistry at work. Hydrogen atoms colliding, molecules spinning, the kind of noise you'd expect from something so enormous, so ancient, and so seemingly chaotic. But every so often, something cuts through the noise, a signal that doesn't belong. A burst of energy that defies explanation, a pattern that repeats just enough to make you wonder, is someone or something out there trying to get our attention? In this video, we're going to explore 25 of the most compelling, mysterious, and downright bizarre signals ever detected from these interstellar clouds. Some last only milliseconds, others pulse with cryptic regularity. A few even seem to carry mathematical signatures that stump our brightest minds. We'll travel from the wow signal that shook the astronomy world in the late 70s to strange repeating bursts that might be evidence of exotic physics or something even more extraordinary. So sit back, open your mind, and get ready. We're about to dive into one of the greatest mysteries in modern science. Of all the strange whispers from the cosmos, none has captured our collective imagination quite like the wow signal, detected on a warm August evening in 1977 by the Big Ear radio telescope at Ohio State University. This single, immense burst of radio energy was so extraordinary that the astronomer who found it, Jerry Amon, scribbled "wow" right on the printout. That single, excited word gave the signal its famous name, and it's a puzzle that has both fascinated and frustrated scientists ever since. For decades, the leading theory pointed toward a potential origin in the constellation Sagittarius, but newer analysis suggests a far more intriguing and perhaps even more profound source: a passing hydrogen gas cloud. The signal itself was almost unbelievably perfect. It roared in at precisely 1420 MHz. Now, why is that number so significant? In astronomy, it's known as the hydrogen line. It's the specific, natural frequency emitted by neutral hydrogen atoms as they drift through the void. It's the universe's most basic radio station, a fundamental channel that any civilization with a rudimentary understanding of physics would know to listen to, and more importantly, to broadcast on if they wanted to be found. It's the cosmic equivalent of shouting "hello" in the most universal language we know. The printout from that night tells the story visually. A string of alphanumeric codes represents the signal's strength, and right there, for a full 72 seconds, the exact duration the Big Ear telescope could focus on a single point in the sky, the readings went off the charts. The sequence, 6EQUJ5, spiked to a value 30 times louder than the background noise of deep space, and then, just as suddenly as it appeared, it vanished. Despite countless attempts to hear it again, the wow signal never repeated. It was a one-time event, a single, deafening shout in an otherwise silent forest. This is where the mystery deepens with the gas cloud theory. Imagine one of these massive, drifting clouds of primordial hydrogen, cold and dark. If such a cloud were to pass between a distant, natural source of radio waves like a quasar or a pulsar and our telescopes, it could act like a cosmic lens. The cloud's own hydrogen could focus and amplify that signal, creating a temporary, incredibly bright flash tuned perfectly to the hydrogen line frequency. It would be a magnificent, natural cosmic illusion, But here's the catch: we've never observed a gas cloud behave in quite this way before. If that is the answer, it means we've discovered an entirely new astronomical phenomenon. And if it isn't, then we're left with that original, thrilling question from 1977. What or who said, "Wow"? If the wow signal was a deafening shout, then our next mystery is a series of faint, erratic whispers that has proven equally frustrating to decipher. It's known by a name that only an astronomer could love, SETI 02+14a. This signal was not discovered by a single person peering at a printout, but by millions of home computers around the world, part of the ambitious SETI at Home project. In 2003, this distributed network of screensavers analyzing radio telescope data flagged something truly peculiar, a signal that was detected not once but 3 separate times, each instance a little different from the last. What made SETI 02+14 so compelling was its behavior. The signal exhibited a property known as frequency drift. Think of it like this. If you listen to a siren on a passing ambulance, the pitch seems to change as it moves toward you and then away. This is the Doppler effect. The signal from SETI 02+14 did the same thing with its radio frequency, shifting in a way that strongly suggested its source was on a rapidly moving planet, perhaps orbiting a distant star. This was exactly the kind of signature SETI researchers had been hoping to find, a potential technosignature, a hallmark of technology. But the plot, as it always does in these mysteries, quickly thickened. When astronomers pointed their most powerful instruments toward the origin point, near the border of the constellations Pisces and Aries, they found nothing. No star, no planet, no galaxy. Just the apparent emptiness of interstellar space, punctuated by the faint presence of diffuse gas clouds. It was like picking up a clear, intelligent radio transmission and tracing it back to the middle of a remote, uninhabited desert. The very characteristic that made it interesting, the frequency drift hinting at a planet, was undermined by the complete lack of any star for that planet to orbit. So what could it be? The usual suspects don't fit the bill. A pulsar, for instance, is a spinning neutron star that emits beams of radiation, creating a perfectly repeating pulse. But SETI 02+14 was not a clean, metronomic beat. Its signal was messy, drifting, and only appeared those 3 times. Other natural phenomena, like cosmic masers, which are naturally occurring amplifiers of radio waves within gas clouds, also fail to explain the specific drifting frequency pattern. This signal occupies a strange middle ground, possessing a characteristic that feels artificial while emanating from a location that seems utterly natural and barren. It remains an open case, a ghost in the machine of cosmic listening, reminding us that sometimes the most tantalizing clues are also the most elusive. Just when we thought the cosmos had shown us all its cards, along came a discovery so explosive and so brief it rewrote the rules of the game. Buried in archival data from the Parkes Radio Telescope in Australia was a single spike of energy so powerful it defied all classification. Found by astronomer Duncan Lorimer and his student David Narkevic in 2007, this event lasted a mere 5 milliseconds. In the blink of an eye, this burst released more energy than our sun puts out in over a month. This was the first official detection of a phenomenon we now call a fast radio burst, or FRB, designated FRB 010724 for the date it was recorded. What made the Lorimer burst so revolutionary wasn't just its raw power, but a specific fingerprint embedded within the signal itself. As the burst traveled across unimaginable distances, its higher frequencies arrived at our telescopes a fraction of a second before its lower frequencies. This effect, called dispersion, is caused by the signal plowing through clouds of free-floating electrons in interstellar and intergalactic space. By measuring this dispersion, astronomers can essentially count the number of atoms the signal bumped into on its journey, giving them a cosmic yardstick to estimate distance. The reading for the Lorimer burst was off the charts. It was so high that the only possible conclusion was that this incredible flash did not originate in our galaxy. It came from billions of light years away, making it the first evidence of a truly extragalactic radio transient of this kind. This revelation immediately pointed toward events of almost unimaginable violence. The initial and still leading theory involved the cataclysmic death of a supermassive neutron star. Picture two of these incredibly dense stellar remnants, each one a city-sized object containing more mass than our Sun, locked in a final, spiraling dance of mutual destruction. Their collision would create a black hole in a spectacular flash of energy, and the surrounding environment is key. These events don't happen in empty space. They occur within the vast, expanding clouds of gas and dust left over from the supernova explosions that created the neutron stars in the first place. This nebulous region could act as a powerful lens or an amplifier, focusing and shaping the radio wave blast into the intensely bright, milliseconds-long burst we detected. Another compelling suspect is the magnetar, a type of neutron star with a magnetic field SO Chinese letter, it's almost incomprehensible. A starquake on the surface of one of these monsters, a sudden cracking of its ultra-dense crust, could unleash a flare of energy that, when it erupts through the magnetar's own surrounding cloud of charged particles, could be transformed into the kind of radio burst that stops astronomers in their tracks. The Lorimer burst was a solitary event, a single shout from the distant cosmos. It showed us that the universe is capable of producing fleeting, incredibly energetic phenomena that we are only just beginning to detect. It opened a new window onto the most extreme physics, all playing out within the beautiful, chaotic nurseries of gas and dust that fill the voids between galaxies. While the Lorimer burst was a singular, explosive event, some of the most perplexing signals from the cosmos are not shouts but rhythms. They are the metronomic beats that echo across light years with a precision that can feel unnervingly artificial. This was the exact experience of a young graduate student named Jocelyn Bell Burnell in 1967. While reviewing data from a radio telescope she helped build, she noticed a peculiar, repeating signal. It pulsed with such perfect, unwavering regularity, once every 1.337 seconds, that it defied all known natural explanations. The source was so clock-like, so seemingly engineered, that a team half-jokingly labeled it LGM-1 for Little Green Men. The idea that they might have stumbled upon a beacon from an advanced civilization was not entirely far-fetched. In a universe filled with the chaotic noise of stellar explosions and the random hiss of cold gas, a perfect, repeating pulse stands out like a strobe light in a fog. The team secretly considered the possibility of a planetary navigation system or an interstellar homing signal. It was a moment of tremendous excitement and profound anxiety, the kind of discovery that could redefine humanity's place in the cosmos. But the truth, once uncovered, was in many ways even more extraordinary. LGM-1 was not a beacon built by aliens. It was the first identified pulsar, a rapidly spinning neutron star, the super-dense corpse of a massive star that went supernova, blasting out beams of radiation from its magnetic poles like a cosmic lighthouse. This historic case of mistaken identity offers a crucial lesson. Nature is a brilliant engineer, capable of producing patterns so precise they mimic technology. And this brings us back to the silent, drifting gas clouds. Within these nebulous regions, a natural process can occur that creates signals startlingly similar to those early pulsar readings. It's called a cosmic maser. The word maser stands for microwave amplification by stimulated emission of radiation. It's the natural predecessor to the laser, but instead of producing a beam of light, it amplifies specific microwave or radio frequencies. Here's how it works in a gas cloud. Imagine a vast cloud of molecules like water or hydroxyl, being energized by the intense radiation from a nearby young star or the shockwave from a stellar explosion. This energy pumps the molecules into a higher, excited state. When a passing radio wave of the right frequency travels through this pumped-up cloud, it stimulates those excited molecules. They release their stored energy, amplifying that original radio wave into an intensely bright, narrow beam signal. And if the source of the energy, like a rotating star or an orbiting binary system, is periodic, the resulting maser emission can pulse with a regularity that looks for all the world like a deliberately engineered broadcast. This natural maser action provides a brilliant explanation for many repeating signals from gas-rich regions. Yet, some rhythmic whispers from the clouds continue to defy such neat categorization. Astronomers have detected periodic signals emanating from within dense molecular clouds that don't neatly align with any known pulsar or maser system. The rhythms are there, clear and persistent, but the underlying engine remains hidden. The gas cloud itself may not be the source but rather a screen, its molecules amplifying and perhaps even modulating a signal from an object we cannot yet see, a hidden neutron star with an unusual spin, a swirling disk of material around a protostar, or even something entirely new. The ghost of LGM-1 reminds us that when we hear a perfect cosmic rhythm, the answer is likely a stunning natural phenomenon we have yet to fully understand. A reminder that the universe's ability to surprise us is truly infinite. Moving from the steady, rhythmic pulses of cosmic masers, we encounter a signal so powerful and so specific that it reignited the debate over intelligent life in the universe for a brief, electrifying moment. In 2015, the Ratan 600 radio telescope in Russia detected a strong, narrow-band signal emanating from the vicinity of a star known as HD 164595, located in the constellation Hercules. The news, when it leaked to the public a year later, sent a jolt of excitement through the scientific community and the world at large. Here was a signal that seemed to tick all the boxes for a potential technosignature. The star itself is a compelling target. It's a sun-like star, roughly the same size and brightness as our own, and we know it hosts at least one Neptune-sized planet. While that world orbits too close to be habitable, the possibility of other, undiscovered rocky planets in the system made it a prime candidate in the search for extraterrestrial intelligence. The signal detected was a spike at 11 GHz, a frequency often associated with military and satellite communications here on Earth. Its strength was perhaps the most staggering aspect. If this broadcast was indeed coming from an isotropic beacon, a transmitter sending signals out in all directions equally, the energy required would be truly astronomical, on par with the total energy consumption of our entire civilization. This suggested a Kardashev Type II civilization, one capable of harnessing the entire power output of its star. Yet, as with so many of these mysteries, the initial excitement was followed by the sobering process of follow-up observation. Teams from the SETI Institute used the Allen Telescope Array to stare at HD 164595 for days, listening intently across a wide range of frequencies. The result was a profound and telling silence. The signal never returned. This one and done nature is a hallmark of many unexplained cosmic events, pointing investigators away from a persistent artificial source and toward a transient natural one. The most plausible explanation, and one that directly involves the interstellar medium, revolves around a phenomenon called gravitational microlensing. Imagine a distant, powerful, but entirely natural source of radio waves, such as a quasar. Now, imagine a faint, drifting cloud of hydrogen gas passing directly through the line of sight between that quasar and our telescopes here on Earth. According to Einstein's theory of general relativity, the mass of that gas cloud, however diffuse, would warp the fabric of space-time around it. This warping would act like a lens, briefly focusing the faint radio waves from the distant quasar and amplifying them into a sharp, bright, and highly directional spike, a cosmic flash in the pan that appears to come from the location of the lens itself, which in this case was the region around HD 164595. The cloud itself would be completely invisible to us, but its gravitational effect would be very real, creating a perfect illusion of a powerful local transmission. This theory elegantly explains the signal's singular nature and its incredible strength, but it remains just that, a theory. We lack conclusive evidence that such a microlensing event occurred at that precise moment. It highlights a recurring theme in our quest. The interstellar medium is not empty. It is filled with these invisible, drifting clouds that can act as cosmic pranks, bending, amplifying, and distorting the light and radio waves that pass through them. They are the universe's great illusionists, capable of creating signals that mock our hopes and challenge our understanding, reminding us that nature's toolbox is far more diverse and clever than we often presume. While the signal from HD 164595 was a distant and fleeting mystery, the search for cosmic company took a shockingly personal turn just a few years later, with a signal that seemed to come not from light years away, but from our own celestial backyard. In 2020, the Breakthrough Listen project, a massive scientific initiative dedicated to finding evidence of technological life, was observing our closest stellar neighbor, Proxima Centauri. This red dwarf star is known to host at least 2 planets, one of which, Proxima Centauri b, orbits within the star's habitable zone where liquid water could theoretically exist. The idea of finding a signal from a potentially habitable world a mere 4.2 light-years away was the ultimate dream, and for a brief, breathtaking moment, it seemed that dream might have come true. The project's algorithms flagged a signal they named BLC-1 for Breakthrough Listen Candidate 1. On the surface, it was everything researchers were hoping to find. It was a narrow-band signal concentrated around 982 MHz. In our world, that's a frequency cluttered with human technology, aircraft, and satellite communications. But the key was that this frequency was conspicuously empty of any local transmissions at the time of detection. More importantly, the signal exhibited a distinct Doppler drift. Its frequency changed over time in a smooth, curving pattern, precisely what you would expect if the transmitter was located on the surface of a planet orbiting its star, first moving toward us as its world rotated into view, and then away as it disappeared behind the star. The discovery sent a wave of cautious euphoria through the team. This wasn't just another strange blip from the depths of space. This was a signal with seemingly intelligent characteristics coming from the star system next door. The possibility of a local, human-made explanation was painstakingly investigated and ruled out. It didn't match the signature of any known satellite or aircraft. For a short while, BLC-1 stood as the most compelling candidate for an extraterrestrial technosignature ever detected, but the universe, it seems, is a master of disguise. The most plausible explanation for BLC-1, after extensive analysis, points not to a planet, but to the complex interplay of human technology and the subtle effects of the interstellar medium itself. The leading theory suggests the signal was actually a highly distorted form of radio frequency interference from right here on Earth. Imagine a simple, low-power electronic device, something as mundane as a faulty computer oscillator or a cheap walkie-talkie, transmitting a faint signal. This signal could have bounced off the ground or off a metal structure near the telescope and entered the receiver at an odd angle. Now, here's where the interstellar medium plays its clever trick. As this reflected, human-made signal traveled through the turbulent layers of our own atmosphere and the tenuous plasma of our solar system, its frequency could have been subtly shifted and modulated. The complex motion of the telescope as it tracked Proxima Centauri, combined with these propagation effects, may have imparted that smooth, curving Doppler drift onto the signal, making it perfectly mimic the expected signature of a transmitter on a distant, orbiting world. It was a perfect storm of terrestrial contamination and natural physics, creating a phenomenal illusion that precisely matched what scientists were searching for. The case of BLC-1 is a powerful lesson in humility and meticulous science. It demonstrates that the very medium through which signals travel, the soup of particles, magnetic fields, and plasma that fills even our local space, can act as a cosmic editor, subtly altering transmissions in ways that can deceive our most sophisticated equipment. It underscores that the greatest challenge in this search may not be hearing the signals, but correctly interpreting them, and always remembering that the space between the stars is never truly empty or silent. It is an active participant in the story, capable of weaving whispers out of nothing and turning our own noise into a tantalizing but ultimately false hello. Deep within the sword of the constellation Orion, a region famous for its stunning nebulae and stellar nurseries, another kind of wonder has been consistently repeating for years, and it defies every attempt to label it. Known to researchers as the Tarantula signal, this transmission has been detected on multiple occasions, and each time it presents a set of properties so unusual that it sits stubbornly in a category all its own. Unlike the one-off bursts and fleeting whispers we've explored, the Tarantula signal is a persistent visitor, returning to our telescopes from the same patch of sky within the vast Orion molecular cloud complex. This isn't a random event, it's a recurring feature of that cosmic neighborhood, and its characteristics are what truly set it apart. The first and most telling clue is its polarization. Most natural cosmic radio sources emit waves that are randomly polarized, meaning the waves oscillate in a jumble of different directions, like a crowd of people waving their hands in every which way. The Tarantula signal, however, is highly polarized. Its waves are aligned, oscillating in a single, clean, precise plane. This kind of organized, structured emission is often a hallmark of technology. Think of a laser beam compared to the scattered light of a light bulb. In nature, such precise polarization is rare and typically only occurs under extreme and specific conditions, like in the powerful magnetic field surrounding certain neutron stars. But the Tarantula signal doesn't match the profile of any known pulsar or magnetar. Its spectral signature, the unique fingerprint of its energy across different frequencies, is unlike any catalogued astrophysical object. It doesn't have the clean, sharp peaks of a maser or the broad, chaotic sweep of a stellar flare. It's something else entirely, a spectral shape that doesn't correspond to the emission lines of hydrogen, hydroxyl, or any other common molecule we'd expect to find in a gas cloud. This forces astronomers to consider more exotic possibilities. Could it be the signature of a natural process we haven't yet discovered? Or does its structured, polarized nature point toward a technological origin, a beacon deliberately designed to stand out against the natural background noise of the galaxy? To understand how such a signal could reach us with such clarity, we need to picture its journey. Imagine the signal originating from a source deep within the Orion cloud, a region so thick with gas and dust that visible light cannot penetrate it. As this radio wave begins its multi-thousand-year voyage toward Earth, it doesn't travel through a uniform void. It must navigate a labyrinth of varying densities, passing through incredibly dense, cold knots of molecular gas, then through warmer, more diffuse regions of ionized plasma. Each of these environments interacts with the radio wave in a different way. Denser pockets of gas can actually act as a natural amplifier through a process called stimulated emission, boosting the signal's strength at specific frequencies. Conversely, they can also scatter and distort the wave, potentially imprinting their own complex patterns upon it. This interaction with the interstellar medium could be the key to the signal's strange properties. The specific path the signal takes through the cloud might be sculpting its polarization and refining its spectral shape, transforming a simpler emission into the complex and puzzling transmission we ultimately detect. It's possible we are not hearing the signal in its original form, but rather a version of it that has been filtered and focused by the very gas cloud that hides its source. This leaves us with a profound and tantalizing mystery. Is the Tarantula signal evidence of a new type of astrophysical object, one whose physics we have yet to understand, hidden within a stellar nursery? Or are we listening to an amplified, distorted echo of something else entirely, a message that has been encoded and then reforged by its passage through the cosmos, waiting for us to learn how to truly decode it? While the Orion cloud presents us with a recurring and structured mystery, our search for the universe's secrets takes us to another, much closer stellar nursery, one filled with its own set of anomalous whispers. Just over 400 light-years away within the constellation Taurus lies one of the nearest and most studied star-forming regions to Earth, the Taurus molecular cloud. This vast, dark nebula is a cosmic laboratory where new stars are being born en masse, surrounded by swirling disks of gas and dust that may one day coalesce into planets. For astronomers, it's a front-row seat to the process of creation. But amidst the predictable cacophony of stellar birth, they've detected something far less predictable, a series of strange, unexplained radio emissions that seem to defy our current understanding of chemistry and physics. These aren't the powerful, one-off bursts we've encountered before. The Taurus anomalies are more like subtle, persistent glitches in the cosmic background noise. They manifest as sharp, narrow spikes at very specific frequencies. Imagine tuning an old analog radio and hearing a clear, strong signal on a frequency that, according to all your manuals, should be broadcasting nothing but static. That's the essence of the mystery here. The spikes occur at frequencies that do not correspond to the known rotational or vibrational transitions of any common molecules we expect to find in such a cloud, like carbon monoxide, ammonia, or cyanide. It's as if the cloud is broadcasting on channels we didn't know existed. Scientists have proposed two compelling, yet profoundly different, explanations for these signals. The first possibility is that we are witnessing unknown chemical processes at work. Within the extreme cold and high density of these molecular clouds, complex chemistry can occur on the surface of microscopic dust grains, building molecules that are difficult or impossible to create in Earth laboratories. The anomalous frequencies could be the signature of these exotic, large molecules, perhaps long-chain carbon compounds or prebiotic molecules that are the building blocks of life, rotating or vibrating in ways we haven't yet catalogued. The Taurus cloud could be a vast chemical factory, and we are only just learning to read its complex product list. The second, and far more thrilling, possibility is that these signals are evidence of exotic physics. Some theorists have suggested they could be the faint signature of actions. Actions are hypothetical, ultralight particles that are a leading candidate for the mysterious dark matter that makes up most of the mass in the universe. According to some models, these particles could theoretically interact with the immensely strong magnetic fields surrounding protostars within the cloud, converting into photons of very specific, predictable frequencies. If true, detecting these signals wouldn't just be solving a radio mystery. It would be our first direct detection of a dark matter particle, a discovery that would fundamentally reshape modern physics. Each unexplained spike from Taurus, then, is a potential window into the 95% of the universe that currently remains hidden from our view. Amidst the specific mysteries of individual clouds, there is a broader, more profound search happening across the entire sky, one that focuses on a specific band of radio frequencies that many scientists consider to be the universe's most promising watering hole. This band, stretching from 1420 MHz to 1662 MHz, is bookended by two of the most fundamental frequencies in all of cosmos. On one end, you have the emission line of neutral hydrogen, the most abundant element in the universe. On the other, the emission line of the hydroxyl molecule, a key component of water. Together, hydrogen and hydroxyl form HOH, or water. This region is poetically and strategically known as the water hole. It's a frequency band that many believe represents a universal channel for communication. Any technological civilization that has grasped basic astronomy would understand the significance of these frequencies. It's a quiet part of the radio spectrum, relatively free of the natural background noise that plagues other frequencies, making it an ideal place to both listen and broadcast. For decades, SETI initiatives have focused a huge amount of their effort right here, in this quiet oasis in the radio desert. And within this special range, we have indeed found signals. But as always, the universe is more complicated than we hope. Some of the most compelling detections from the waterhole don't come from the direction of stars, but from the vast, dark molecular clouds themselves. These signals appear as sharp, narrow spikes on a spectral graph, tall, thin lines rising from a flat baseline of noise. When you compare them to the known signals from natural cosmic masers, the differences are striking. A natural water maser, for instance, might appear as a broader, slightly messy hump of emission, caused by the signal traveling through turbulent gas and being amplified over a slightly wider range of frequencies. These anomalous signals, however, are razor-sharp. Their bandwidth is incredibly narrow, as if someone had tuned a radio transmitter to a single, perfect note and held it. This narrow bandwidth is one of the key characteristics that SETI looks for, as it is extremely difficult for natural processes to achieve without some form of sophisticated technology. The other puzzling aspect is their stability. Natural masers are chaotic. Their strength can fluctuate wildly as the conditions in the cloud change. The energy from a young star varies or the density of the gas shifts. These unexplained signals, however, have been observed to remain at a constant intensity for remarkably long periods, sometimes for hours. This kind of unwavering stability is again a potential hallmark of an engineered source, a beacon designed to be noticed. Yet they eventually fade away, never to be seen again, ruling out a persistent artificial source like a dedicated beacon. So if they're not aliens, what could possibly create such a perfect, stable, yet temporary signal within a gas cloud? The leading theory brings us back to the incredible power of natural amplification, but with a fascinating twist. Imagine a distant, steady source of radio waves, something like a quasar, which is an active supermassive black hole at the center of a galaxy, pouring out energy. That signal, by the time it would normally reach us, would be incredibly faint, lost in the general background static of the universe. But if, on its multi-million-year journey, it passes directly through a particularly dense and well-organized knot of gas within a molecular cloud that is perfectly pumped with energy, a spectacular bit of cosmic luck can occur. This specific pocket of gas could act as a natural maser cavity, but one that is exceptionally uniform and stable for a short time. As the quasar's faint signal passes through, the cloud doesn't just amplify it randomly. It amplifies it with extreme precision, focusing on one specific frequency within the water hole and sharpening the broad, natural signal into that telltale narrow spike. The stability of the signal wouldn't come from the source, but from the lens, the brief period when that specific knot of gas was perfectly configured to act as a universal amplifier. It would be a fleeting cosmic coincidence, a natural radio telescope of unimaginable scale focusing a distant whisper into a shout that we can hear, before the turbulent cloud moves on and the signal vanishes forever. This elegant explanation accounts for the artificial seeming properties without requiring a technological origin, showcasing once more that nature's ability to mimic design is one of the most awe-inspiring forces in the universe. Now let's venture into the profound darkness between the stars, where some of the most mysterious signals of all seem to emanate from nothing at all. Astronomers have long mapped the universe by the light of its stars and galaxies, but what happens when our telescopes pick up a powerful radio broadcast from a patch of sky that appears to be completely, utterly empty? This is the enigma of the so-called dark galaxy radio emissions, signals that challenge the very foundation of what we believe a galaxy to be and force us to reconsider the invisible architecture of the cosmos. The story often begins with a large-scale radio survey, like those conducted by the Arecibo Observatory or the Low Frequency Array, or LOFAR. These projects meticulously scan vast swaths of the sky, building a radio map of the universe. Most of the time, a bright radio source corresponds to a visible object, a distant quasar, a bustling star-forming galaxy, or a supernova remnant. But every so often, they find a signal that has no optical counterpart. Point the world's most powerful optical telescopes, like Hubble or the Very Large Telescope, toward that exact coordinate, and you see nothing, just the black, empty void of intergalactic space. It's as if you're hearing a roaring crowd from the other side of a wall, but when you open the door, the room is vacant. One leading hypothesis for these ghostly transmissions is that we are detecting the faint, diffuse signals from dark matter galaxies. According to our most successful models of cosmology, the universe should be teeming with small, satellite galaxies orbiting larger ones like our Milky Way. But we don't see nearly as many as we predict. This is known as the missing satellites problem. The theory suggests that many of these dwarf galaxies are made almost entirely of dark matter, with very few, if any, stars. Without stars, they emit no visible light, rendering them invisible to optical telescopes. But they would still contain vast reservoirs of neutral hydrogen gas, the fuel for star formation that never ignited. This primordial hydrogen, left over from the Big Bang, would still emit its characteristic 21-centimeter wavelength radio signal. If such a dark galaxy were to drift through a region of intense intergalactic radiation or interact with the gravitational pull of a visible galaxy, it could stimulate that hydrogen to emit a radio signal we can detect, a faint whisper from a galaxy of shadows. But the interstellar medium itself might be the source of an even more exotic illusion. Computer simulations of the cosmos are now so sophisticated they can model the behavior of dark matter on a grand scale, tracing how it forms vast, intricate webs and halos that span millions of light years. These simulations show that streams of ordinary baryonic matter, the gas that makes up stars and planets, can become gravitationally caught and stretched within these halos of dark matter. As this gas is pulled and compressed, it heats up and its particles become agitated. This turbulent motion can generate weak radio emissions through a process called Bremsstrahlung radiation, where charged particles like electrons are decelerated as they interact with other matter. However, the emissions we detect from these empty patches of sky are often far stronger than what standard models of gas physics can explain. This has led scientists to propose that something else is supercharging this process. The answer might lie in a phenomenon known as dark matter annihilation. Some theories propose that dark matter particles are their own antimatter counterparts. When two of these particles collide, they could annihilate each other in a flash of energy, producing a shower of secondary particles like electrons and positrons. This sudden injection of high-energy particles into a surrounding cloud of hydrogen gas would act like a power surge, energizing the gas and causing it to emit radio waves far more intensely than simple gravitational heating ever could. What we are hearing, then, could be the death cry of dark matter itself, a signal generated by the annihilation of particles we cannot see, within a structure we cannot directly observe, illuminating a ghostly galaxy that officially doesn't exist. These dark galaxy candidates force a dramatic reevaluation of the interstellar and intergalactic medium. We can no longer think of the space between galaxies as a true void. It is a dynamic arena where dark matter structures govern the movement and behavior of ordinary matter in ways we are only beginning to comprehend. The radio signals from these empty fields are not mere curiosities. They are potential signposts pointing toward a hidden, dark universe operating in parallel to our own. They suggest that galaxy formation is not a process reserved for bright, starry behemoths, but also occurs in secret, creating dark, gaseous realms that are the silent, invisible majority of the cosmic population. Each unexplained emission is a clue, a piece of a puzzle that could ultimately reveal the nature of the dark matter that binds the entire cosmos together. Among the most brilliant and bewildering phenomena within these stellar nurseries are cosmic mazes, and nowhere are they more spectacular than within the great Orion molecular cloud. Here, vast regions of gas are energized by the intense ultraviolet radiation streaming from newborn, massive stars like those in the famed trapezium cluster. This energy pumps specific molecules like water and methanol into an excited state, setting the stage for nature's own lasers to ignite. But some of these natural amplifiers are behaving in ways that defy our physical models, broadcasting signals of such immense power that they leave astronomers searching for a missing piece of the puzzle. The most prominent of these anomalies involve methanol masers. Methanol, a simple alcohol molecule, can be stimulated to emit intense microwave radiation at extremely precise frequencies, most notably at 669 MHz and 12.2 GHz. In most star-forming regions, the strength of this maser emission aligns neatly with the amount of available methanol and the power of the pumping source, usually a nearby protostar. But in specific, dense knots within the Orion cloud, the observed emission is thousands of times more powerful than any standard model can account for. It's the difference between expecting the gentle glow of a candle and instead being confronted by the blinding beam of a searchlight. The mystery deepens when we examine the behavior of these supermasers. They don't just shine with unwavering power, their intensity can fluctuate over periods of days, weeks, or months. This variability itself isn't unusual. Masers are known to flicker as their energy sources change. But the patterns observed in Orion are strange. Some show a rhythmic, almost periodic dimming and brightening, while others erupt in sudden, unpredictable bursts of energy. This suggests that the standard maser pump, which relies on steady stellar radiation, isn't the whole story. Something else, something dynamic, must be supercharging these natural amplifiers. One compelling theory points to the role of shockwaves. Imagine a young, volatile star unleashing a powerful flare or a jet of material at nearly relativistic speeds. This jet could slam into a nearby pocket of gas rich in methanol molecules. The impact wouldn't just gently pump the molecules, it would violently compress and heat the gas, creating a chaotic, high-energy environment far more efficient at exciting the methanol. This temporary, explosive interaction could generate a maser flash of extraordinary brightness, a cosmic stroke of lightning that briefly outshines everything else in the region. Once the shockwave passes, the maser would fade back to its normal state, explaining the transient nature of these ultra-bright events. Another, more speculative idea involves the hidden architecture of the cloud itself. What if these anomalously powerful masers aren't being pumped by a single source, but are instead being fed by multiple energy streams? A dense core might be situated at a perfect crossroads, receiving pumping radiation from several young stars simultaneously. Or the geometry of the gas cloud could be acting as a natural resonant cavity, trapping maser photons and forcing them to bounce back and forth, stimulating more and more emissions with each pass in a runaway feedback loop of amplification. We may be looking at a natural version of a laser cavity, engineered by chance and chaos to produce a beam of startling coherence and power. These methanol maser anomalies are more than just a curiosity, they are vital diagnostic tools. Their intense light acts as a probe, allowing us to study the physical conditions, the temperature, density, and magnetic field strength, in regions of star formation that are otherwise too obscured by dust to observe directly. By understanding why they shine so brightly, we learn about the violent, energetic processes that govern the birth of stars and planets. Each unexplained fluctuation is a clue, a signpost pointing toward a more complex and dynamic reality within these cosmic nurseries, reminding us that even nature's most well-understood mechanisms can still hold spectacular secrets. Yet as we expand our listening beyond the specific frequencies of the water hole, we encounter signals of an entirely different character. Not sharp, high-pitched whistles, but deep, rumbling whispers that seem to emanate from the very fabric of space itself. These are the ultra-long wavelength radio emissions, and one of the most captivating sources is the colossal Barnard's Loop, a vast, arc-like emission nebula that curves through Orion like a cosmic smile, stretching over 300 light-years across. This structure is a relic of ancient supernova, a titanic bubble of ionized gas glowing from the energy of long-dead stars. But it's not just emitting visible light, it's humming with a low-frequency radio song that presents a profound puzzle. The signals detected from Barnard's Loop are not like the transient bursts or narrow-band spikes we've discussed. They are persistent, diffuse, and incredibly low in frequency, which means they have very long wavelengths, sometimes measuring kilometers from peak to peak. To put that in perspective, the radio waves that bring music to your car are only a few meters long. These emissions from the loop are the cosmic equivalent of a deeply resonant bass note, one that rumbles through the interstellar medium rather than cutting across it. This presents an immense challenge for detection, as these kilometer-long waves require telescopes of a colossal scale, often using networks of antennas spread across entire continents to piece the signal together. So what could possibly generate such a deep, pervasive hum from a cloud of gas? The prime suspect is one of the most fundamental forces in the cosmos: magnetism. Barnard's Loop is not a placid pool of gas. It is a dynamic structure seething with turbulent motion and laced with powerful magnetic fields. One compelling process is synchrotron radiation. Imagine an electron ripped from its atom by the violent energy of a past stellar explosion, now caught in the grip of this magnetic field. The field forces the electron to spiral along its lines at nearly the speed of light. This wild, corkscrewing motion causes the electron to shed energy, emitting it as a broad, continuous spectrum of radio waves, predominantly at these very low frequencies we detect. It's a natural particle accelerator on a staggering scale. However, the sheer intensity and specific structure of the whispering signals from the loop suggest that standard synchrotron radiation might not be the full story. The emissions are stronger and more structured than simple models predict, hinting at a more exotic or efficient acceleration process at work. Some astrophysicists theorize that the chaotic environment within the loop is generating gigantic shockwaves and turbulence. These are not like sonic booms on Earth. They are ripples in the fabric of magnetized plasma that can act like enormous natural particle slingshots. As charged particles surf across these shock fronts, they can be accelerated to incredible energies far more efficiently than in a steady magnetic field. When these supercharged particles then interact with the magnetic fields, they produce a more intense and complex radio whisper than we would otherwise expect. Another fascinating possibility involves the interaction of the loop itself with its environment. Barnard's Loop is not an isolated island. It is expanding into the surrounding interstellar medium, pressing against cooler, denser regions of neutral hydrogen. At this turbulent boundary layer, the magnetic fields from the hot, ionized gas of the loop can become tangled and reconfigured with the fields in the cooler cloud. This magnetic reconnection, a process where magnetic field lines break and rapidly reconnect, releases enormous amounts of energy, violently flinging particles outward and potentially generating those telltale low-frequency waves. The entire structure could be acting as a massive, slow-motion engine, converting magnetic energy into radio emissions through its ongoing collision with the galaxy. The deep, rhythmic whispers we detect may be the sound of this colossal engine at work, a hum that has continued for millions of years, telling the story of an ancient explosion that is still shaping its corner of the cosmos. Traveling north from the turbulent beauty of Orion, we find ourselves in the constellation of Perseus, staring into the vibrant heart of another cosmic wonder, the California Nebula. Officially catalogued as NGC 1499, this massive cloud of glowing hydrogen gas stretches over 100 light-years long, its shape eerily reminiscent of the American state it's named for. It's a beautiful and well-studied region, lit by the intense ultraviolet radiation of a brilliant hot star called Xi Persei. For the most part, its emissions are exactly what astronomers would predict, a steady, chaotic hum of energetic processes. But nestled within that predictable noise is a signal that is anything but. It's a rhythmic beat, a series of periodic pulses that arrive with a timing and structure that defies all known natural explanation, standing out against the nebula's background glow like a perfectly steady metronome in a room full of random noise. The pulses from the California Nebula are not like the rapid-fire ticks of a pulsar, which can spin hundreds of times per second. These are slower, more deliberate beats, with periods measured in minutes or even hours. This immediately rules out the spin of a neutron star. Nothing that massive could rotate that slowly without flying apart. Even more intriguing than their tempo is their pattern. The pulses aren't just a simple on-off repetition. They exhibit complex harmonic structures, meaning the main pulse is often accompanied by softer, secondary pulses that are precise mathematical multiples or fractions of the primary period. It's akin to hearing a fundamental musical note and then clearly hearing its perfect octaves and fifths ringing out alongside it. This kind of structured complexity is incredibly rare in nature, where signals tend to be either chaotic and random or rigidly simple. So what cosmic instrument could possibly be playing this strange harmonic song? The leading theory takes us into the dynamic, violent physics of the nebula itself. The entire structure is being shaped and energized by the powerful stellar wind from its central star, Xi Persei. This wind is a supersonic torrent of charged particles screaming outward from the star, and it is constantly slamming into the slower-moving gas of the nebula. Now imagine a single, exceptionally dense knot of gas deep within the cloud. As the stellar wind buffets this knot, it doesn't just sit there. It can begin to vibrate or oscillate, much like a bell ringing after being struck by a clapper. These vibrations wouldn't be random. The dense knot of gas has a natural resonant frequency determined by its size, density, and magnetic field. The impacting shock waves from the stellar wind could set it ringing at this fundamental frequency, and the resulting oscillations could then produce periodic compressions and rarefactions in the surrounding plasma. Each time the gas compresses, it could trigger a burst of coherent radio emission, a pulse. The harmonic patterns could be explained by the knot vibrating not just at its primary frequency, but also at higher order modes, the way a guitar string produces its main note and a series of softer overtones simultaneously. In this model, we are not hearing from a single object, but from the entire nebula itself singing a note as it is played by the relentless force of its central star. To truly appreciate the oddity of this signal, you have to hear it. Through a process called sonification, astronomers can translate these radio pulses into sound waves within the range of human hearing. The result is eerie and beautiful. What you hear is not a static hiss or a random crackle. It's a clear, rhythmic pattern, a low, resonant thump followed by a pause, then another thump, and with careful listening, you can sometimes make out a higher-pitched, quieter tap occurring precisely between the main beats. This audible pattern makes the mystery tangible. It feels structured, almost composed. It's this quality that pushes scientists to consider even more exotic possibilities, such as the idea of a naturally occurring, plasma-based construct within the nebula, a region where conditions are just right for the ionized gas to form a temporary, oscillating cavity that acts like a natural radio transmitter, ringing out into the void with a message not of intelligence, but of pure, complex physics. The California Nebula's pulse is a reminder that even in the well-mapped territories of our galactic neighborhood, the universe still has new ways to make music, and we are only just learning to listen. Deep within the constellation Cygnus, the Swan, lies one of the most massive and turbulent star-forming regions in our entire galaxy, a place known simply as Cygnus X. It's not a single object, but a sprawling complex of colossal molecular clouds, glowing nebulae, and deeply embedded stellar nurseries, all churning together in a cosmic maelstrom of creation. When we point our telescopes toward this region, we expect a certain kind of symphony, the sharp, specific notes of molecular emission lines and the steady hum of thermal radiation from warm dust. But Cygnus X has a much stranger, more powerful song for us. It broadcasts a roar across a huge swath of the radio spectrum, from low frequencies all the way up into the microwave range. This region emits a pervasive, continuous broadband signal that simply shouldn't be there according to our standard models of cosmic physics. This isn't a narrow whistle or a repeating pulse. This is a wall of sound. If most cosmic signals are like a single instrument playing a clear melody, the emission from Cygnus X is the sound of the entire orchestra warming up at once, a chaotic, powerful, and seemingly disordered blast of energy. The key to the mystery lies in its origin. Thermal radiation, which is the kind of emission we get from any warm object like dust or gas, has a very specific and predictable signature. Its intensity smoothly changes across different frequencies. The signal from Cygnus X defies this. Its strength and distribution across frequencies point squarely to a different class of emission altogether, non-thermal radiation. This is the wild, unpredictable energy generated not by heat, but by the frenzied motion of charged particles hurtling through magnetic fields at nearly the speed of light. So what incredible engine is powerful enough to generate this galaxy-sized roar? The prime suspect is the sheer, unbridled violence of the region itself. Cygnus X is a factory for massive stars. These aren't like our calm, middle-aged sun. These are titanic, tempestuous beasts that live fast and die young, pumping out hurricane-force stellar winds and flooding their surroundings with intense ultraviolet radiation. When these fierce winds collide with the surrounding molecular cloud, they don't just gently push the gas aside. They create colossal shockwaves, tsunamis of energy that rip through the cloud, compressing gas, tangled magnetic field lines, and acting like enormous natural particle accelerators. Electrons caught in these maelstroms are whipped to relativistic speeds, and as they spiral madly along magnetic field lines, they shed their immense energy as synchrotron radiation, which manifests as this very broad, non-thermal radio roar we detect. Yet, even the tremendous violence of massive star formation might not be the full story. The intensity and specific structure of the broad-band emission in some parts of Cygnus X are so extreme that some astrophysicists are looking toward even more exotic explanations. One compelling theory involves the presence of thousands of unresolved sources. What if, deep within the dusty veil of the cloud, there are swarms of protostars still in the process of formation, each with its own powerful magnetic activity and jet eruptions? Their combined, overlapping radio shouts could blend together into a single, powerful broadband hum that appears to come from the entire cloud. Another, more speculative idea points to the potential role of cosmic rays, high-energy protons, and atomic nuclei that constantly bombard our galaxy. The dense environments of Cygnus X could be a major source for these rays, and their interactions with the cloud's material could generate a significant portion of this puzzling emission through complex secondary processes. The true beauty and power of this investigation is revealed when we combine the eyes of our different telescopes. A single wavelength image might show a featureless blur, but a composite view weaves a far richer tapestry. In these stunning multi-wavelength portraits, the optical data from telescopes like Hubble shows us the beautiful, sculpted nebulosity, the outer skin of the cloud illuminated and eroded by starlight. The infrared view from observatories like Spitzer peers deeper, revealing the hidden embedded stars and the warm dust that shrouds them. And then, laid over top, the radio data paints the final, crucial piece, the vast, intricate structures of the broadband emission, often tracing out the invisible shock fronts and magnetic field lines where all this incredible energy is being generated. It's in this synergy of vision that we see the full picture, not just a cloud of gas, but a dynamic, violent, and breathtakingly energetic ecosystem, whose full power is expressed in a radio roar we are only just beginning to understand. But if we travel even further south to the magnificent constellation of Carina, we find a stellar nursery that presents a mystery not of sound but of light, or more precisely, the specific colors of radio light that no one can identify. The Tarantula Nebula is one of the largest and brightest nebulae in the night sky, a sprawling cosmic landscape of glowing gas and dark dust pillars where stars are both being born and dying in spectacular fashion. When astronomers train their radio telescopes on this chaotic beauty, they see the expected forest of spectral lines, the unique fingerprints of atoms and molecules as they jump between energy states. Hydrogen, carbon monoxide, ammonia, all the usual suspects are there, creating a predictable map of the nebula's chemistry. But scattered amongst these familiar signatures are a few spectral lines that are complete strangers. They are emission lines at very specific frequencies that do not correspond to any known atomic or molecular transition in any database on Earth. It is as if you were listening to a symphony and heard a single, perfect, beautiful note played by an instrument that doesn't exist. The hunt to identify these spectral interlopers is a fascinating process of elimination that pushes the boundaries of both chemistry and physics. The first and most exciting possibility is that these are the signatures of entirely new molecules, complex compounds formed in the unique laboratories of these nebulae. Dr. Clara Bennett, a molecular spectroscopist, explains the challenge. In the cold, dense cores of these clouds, she says, chemistry operates in ways we can barely simulate. Molecules can form on the surface of icy dust grains, building up long, complex carbon chains or rings that would be highly unstable in an Earth lab. We're talking about things like polyions, carbon chain molecules, or even prebiotic molecules like amino acids. The problem is, we haven't measured the precise radio frequencies for many of these exotic molecules in a laboratory setting, so a line appears in our data from Carina and we simply don't have a reference to match it to. It's like having a key without knowing which lock it opens. Yet another layer to this mystery involves not just new molecules but new states of matter. The environment within a nebula like Carina is extreme, bathed in intense ultraviolet radiation, threaded with powerful magnetic fields, and home to vast shockwaves from stellar winds and supernova. This could be creating conditions that force atoms and molecules into unusual configurations. Perhaps we are seeing the signature of metastable helium or oxygen, atoms that have been pumped into high-energy states that last much longer than usual, allowing them to emit at frequencies that are rare and poorly documented. Or, even more intriguingly, the lines could be evidence of what's known as Rydberg matter, a theorized state of matter where atoms become highly excited and enormous, forming a kind of dense, gaseous crystal that could have its own unique and unrecognized spectral signature. The implications of these unidentified lines ripple outward, touching on one of the most profound questions in astronomy: how do we truly know what's out there? Our entire understanding of the universe's composition is built on spectroscopy, matching the light we receive to the laboratory measurements we've made here at home. The Carina Nebula's mystery lines are a stark reminder that our laboratory is incomplete. They are a direct challenge, a set of cosmic clues pointing toward a richer, more complex interstellar chemistry than we ever imagined, waiting for us to finally build the right tools and conduct the right experiments to give these phantom molecules a name. Soaring high in the tail of the serpentine constellation Serpens, the Eagle Nebula presents one of the most iconic portraits of cosmic creation ever captured. Its famous pillars of creation, those towering spires of gas and dust, are more than just a beautiful Hubble image. They are a dynamic, violent nursery where new stars are actively being born. And it's here, within this chaotic cradle, that our radio telescopes have detected a signal with a most peculiar twist, literally. The radio waves streaming from the heart of these pillars exhibit a strong and unusual form of circular polarization. To understand why this is so strange, let's break that down. Most natural light and radio waves are unpolarized, meaning their waves vibrate in a random, disorganized jumble of directions. Think of it like the scattered light reflecting off the surface of a lake. Linear polarization is more organized, where the waves are all vibrating in a single plane, like light reflecting off a flat, glassy window. Circular polarization, however, is something else entirely. Imagine the wave itself corkscrewing through space, spinning like a drill bit as it travels. This is a much more structured, orderly state, and in the cosmos, it's notoriously difficult to create without a very specific and powerful influence, an incredibly strong and organized magnetic field. When astronomers first mapped this circularly polarized signal from the Eagle Nebula, it immediately suggested that the magnetic fields within the pillars of creation are far more complex and powerful than we ever imagined. We can now use this polarization data to construct stunning 3D visualizations of these invisible magnetic fields. The result is breathtaking. Instead of a chaotic mess, we see the magnetic field lines acting like a cosmic skeleton, tracing the elegant contours of the pillars themselves. These lines are not just passive bystanders, they are integral to the structure, providing crucial support against the overwhelming force of gravity that is desperately trying to collapse the gas into new stars. They are the architectural girders holding up the entire construction site, but the sheer strength of the polarization hints that organized magnetic fields might not be the only player in this game. There's another, more exotic possibility: coherent emission. This is the difference between the chaotic roar of a crowd in a stadium and the unified, powerful chant of that same crowd all singing the same note together. Incoherent emission is what we typically get from hot gas or synchrotron radiation. Every atom or electron is emitting independently, resulting in a messy, unpolarized jumble. Coherent emission is when particles act in concert, emitting their waves in perfect phase, which can produce an intensely bright and highly polarized signal. We engineer this effect for our own technology in lasers and masers. To find it occurring naturally on such a colossal scale is extraordinary. So what natural engine could be generating a coherent, polarized signal within a gas cloud? The most likely candidate is a process called the electron-cyclotron maser instability. Picture a vast region within a pillar where powerful shockwaves from newborn stars have compressed gas and amplified magnetic fields to incredible intensities. Electrons caught in this environment don't just spiral along the field lines. They can become trapped, bouncing back and forth between magnetic mirrors in a natural confinement system. As their population builds up, it can become unstable, and they suddenly release their pent-up energy in a coordinated burst, a super-powered natural maser that emits a tightly beamed, brilliantly bright, and perfectly circularly polarized radio wave. This isn't just a signal, it's a hurricane screaming its signature tune through the magnetic storm of its own birth. The presence of such a phenomenon would completely change our understanding of the star formation process itself. We traditionally see it as a battle between gravity and gas pressure, with magnetic fields playing a subtle background role. But if the Eagle Nebula's polarized whisper is indeed the signature of a giant cosmic maser, it means that magnetic fields are not just supporting structures, they are active, energetic participants. They can focus and channel the violent energy of stellar birth into coherent beams of radiation that can punch through the surrounding dust and gas, potentially influencing the formation of other stars nearby and leaving their unique, twisted signature across light years of space for us to decipher. Now we venture into one of the most visually stunning regions of our galaxy, a place where the chaos of creation is painted across the sky in brilliant hues of pink and red, the Lagoon Nebula. Known as Messier 8, this vast cloud of gas and dust is a bustling stellar factory, home to thousands of young stars. But amidst this beautiful turmoil, our telescopes have picked up something far more fleeting and violent, transient events of such brief, ferocious intensity that they appear and vanish in the cosmic blink of an eye, leaving behind only questions. These are not the steady glows of star formation or the predictable pulses of a distant pulsar. The lagoon's transients are cosmic flashbulbs. They erupt without warning, often lasting mere hours, and release a staggering amount of energy across the radio spectrum before fading back into the nebula's background hum. Their energy profiles are what truly baffle astronomers. A single one of these events can, for its short life, outshine the entire nebula at specific frequencies. To put that in perspective, that's like a single grain of sand on a beach suddenly glowing brighter than the sun. We're talking about energy releases that rival, and in some cases surpass, those of solar flares from our own sun, but they're emanating from deep within a cloud of gas light years across. When a signal this powerful is detected, the first instinct is to compare it to known celestial catastrophes. Could it be a supernova? The sheer power fits, but the timeline is all wrong. A supernova brightens over days or weeks and can remain visible for months. These events are over in hours. A gamma-ray burst, their incredible energy is a match, but gamma-ray bursts are typically singular, universe-spanning events originating from far outside our galaxy. The lagoon's transients are localized, recurring, and seem to be intimately tied to the structure of the nebula itself. They are a completely new class of phenomenon, playing out on a stage we thought we understood. The key to visualizing this mystery lies in time-lapse observations. Imagine a video compiled from years of radio telescope data of the Lagoon Nebula. The vast structure glows with a steady, unchanging light, the calm background of a bustling stellar nursery, and then a pinpoint of light flares into existence. It isn't associated with any known visible star or protostar. Over the next few hours, it brightens dramatically, becoming a brilliant beacon. Just as you begin to wonder what incredible object could be powering it, the light vanishes, leaving the nebula exactly as it was before. These visual records are crucial, proving these aren't instrument glitches or data errors, but real, physical events occurring within the gas cloud. So what could possibly cause such a brilliant, fleeting flash? The most compelling theories all point to the extreme and dynamic environment of the nebula itself. One leading idea involves magnetic reconnection on a titanic scale. Deep within the lagoon, the powerful magnetic fields that thread through the ionized gas can become strained and tangled, storing immense energy like a wound-up rubber band. When the tension becomes too great, the field lines can suddenly snap and reconnect, releasing that stored energy in an explosive flash that accelerates particles to near light speed. This process is well documented on the Sun, causing solar flares, but the scale of the events in the lagoon suggests a magnetic storm of almost unimaginable ferocity. Another fascinating possibility points the finger at young, volatile stars buried within the dusty veil of the nebula. The lagoon is filled with massive, hot O-type stars and their smaller, but even more tempestuous siblings Fu Orionis-type stars. These are infant suns known for going through extreme outbursts, suddenly brightening by a factor of 100 as they voraciously consume material from their surrounding disks. If one of these stars were to unleash a colossal flare or a hyper-powered jet of material, and that jet were to slam into a dense knot of gas in just the right way, the resulting shockwave could generate an intense, temporary burst of radio emission. The signal would be a brief echo of that stellar tantrum, a spotlight flaring on and then off as the shockwave passed through and dissipated. These mysterious flashes from the lagoon remind us that even in our galactic backyard, the processes of star birth are far more violent and unpredictable than we ever dreamed. Just as the Lagoon Nebula captivates with its brilliant flashes, another stellar nursery compels us with a different kind of magic, not raw power, but perfect mathematical order. In the heart of the constellation Sagittarius, the Omega Nebula, or Messier 17, unfurls its vast swan-like shape. This region is a cauldron of star birth, illuminated by the fierce light of massive new stars. But when we listen to it with radio telescopes, we hear something that sounds less like cosmic chaos and more like a carefully composed piece of music. The signals here don't just pulse, they sing in harmony. The data reveals a spectrum that is utterly captivating. Instead of a single, solitary spike at one frequency, we see a series of them. A powerful primary signal stands out, and then, spaced at perfectly equal intervals above and below it, we see its echoes, its harmonics. These aren't random blips, they are precise mathematical multiples of the fundamental frequency. If the main signal is a musical note, these are its perfect octaves, fifths, and thirds, creating a chord of pure radio waves ringing out across light years. Visualizing this on a frequency display is like looking at the harmonic series from a physics textbook. Only this textbook is written across 20 light years of ionized gas. Our first instinct, given the nebula's intense activity, is to look for a natural amplifier, and the prime suspect is a process called a series of resonant cavities. Picture the interior of the Omega Nebula not as a uniform cloud, but as a complex structure of bubbles and shells carved out by the fierce stellar winds of its newborn stars. Imagine a specific shell of gas with a precise thickness and density. This shell can have a natural resonant frequency, much like the air inside a flute has a specific note it wants to produce when you blow across it. Now, as the chaotic radio noise from the central stars passes through this shell, the shell doesn't amplify all of it. It selectively amplifies only the frequencies that match its resonance and the perfect harmonics of that resonance. The shell acts as a natural filter, a cosmic soundboard that takes the random noise of the nebula and sculpts it into a clean, harmonic chord. But the sheer precision of these harmonics pushes us to consider even more exotic natural explanations. Could we be seeing the signature of standing shock waves? The intense radiation and particle winds from the massive stars in M17 are constantly slamming into the surrounding cooler gas, creating vast, stable shock fronts. These are not fleeting explosions, they can be long-lived structures. Theorists have modeled how particles accelerated between two such parallel shock fronts could oscillate, and how the surrounding plasma could vibrate in specific, stable modes. The mathematics shows that these vibrations wouldn't just produce a single frequency. They would naturally generate a whole series of harmonic frequencies, a perfect echo of the harmonic signals we detect. It would be the nebula itself ringing like a bell struck by the relentless force of its own stars. The haunting beauty of these signals inevitably leads to a more profound question. Could such mathematical perfection ever be a sign of intelligence? It's a seductive thought. In human technology, we use harmonics all the time. They are the foundation of music and are crucial in everything from radio transmission to the design of electronic circuits. A deliberate, powerful broadcast might employ harmonics to ensure the signal is received clearly and to distinguish it from natural background noise. The harmonic pattern in M17 is precisely the kind of orderly structure that SETI scientists have long speculated an advanced civilization might use as a beacon. It's a universal language of mathematics that any technological species would presumably understand. However, the cosmos has repeatedly taught us that nature is the most brilliant engineer of all. The lesson of the pulsar, initially mistaken for a beacon, looms large. The harmonic signals from the Omega Nebula almost certainly have a breathtaking natural origin, a phenomenon we are only just beginning to model and understand. They represent a new frontier in astrophysics, where the chaotic nurseries of stars can, under the right conditions, produce patterns of stunning order and beauty. This doesn't make the discovery any less spectacular, it makes it more so. It reveals a universe that is not only vast and violent but also capable of an intrinsic natural music, composed by the interplay of physical forces on a scale we are only learning to hear. Nestled within the constellation Monoceros, the unicorn, the Rosette Nebula is a celestial flower of breathtaking beauty, a sprawling cloud of gas and dust illuminated from within by the fierce young stars of its central cluster. But when we listen closely to this cosmic bloom, we hear a signal that adds a layer of profound mystery to its allure. Emerging from its complex structure is a radio transmission that doesn't just shine with a steady light, it seems to breathe. Its intensity rises and falls in a complex, repeating pattern of amplitude modulation, a rhythmic pulsing that suggests something within the nebula is not just broadcasting, but spinning, vibrating, or oscillating in a deliberate, periodic dance. To understand why this is so unusual, picture the difference between a constant, pure tone and the wavering vibrato of a singer's voice. That vibrato is a modulation, a controlled change in the sound's amplitude or pitch. Most natural cosmic radio sources are like that pure tone, steady, their intensity dictated by the constant, unchanging physics of a hot gas or a spinning neutron star. The modulated signal from the rosette, however, carries the distinct signature of something dynamic. Its repeating pattern of brightening and dimining points to a physical process that is cyclical, a piece of cosmic clockwork operating deep within the nebula's glowing folds. The most logical explanations draw from the nebula's own violent anatomy. At its heart, the bright stars of NGC 2244 blast their surroundings with devastating stellar winds, creating immense pressure that sculpts the gas and drives powerful shockwaves outward through the cloud. One compelling theory suggests these very shockwaves could be the modulator. Imagine a dense knot of gas acting like a celestial lighthouse. As a shockwave spirals outward from the central cluster, it would periodically sweep over this knot, compressing it and causing it to flare brightly in radio waves for the duration of the path. The rotation of the shockwave itself, or its precession around the central stars, could create the precise, repeating interval of the modulation we detect. Visualizing this, we'd see a wave of energy swirling through the nebula, lighting up pockets of gas in a sequential, clock-like pattern. Another strong candidate is a rotating structure, perhaps a dense protoplanetary disk or a jet emanating from a deeply embedded protostar. If such an object were tilted relative to our line of sight, its beam of radio emission would sweep across Earth once per rotation, much like the beam from a lighthouse appears to flash to a distant ship. The period of the modulation would directly correspond to the rotational period of this hidden engine. Animations can bring this to life, showing a narrow, searchlight beam of radiation slicing through the nebula's glow, creating a regular pulse that stands out against the background chaos. Yet, for all the elegance of these natural models, some of the modulation patterns detected in the rosette defy easy classification. The rhythms are sometimes complex, with multiple overlapping periods or asymmetrical shapes to their brightening and dimming cycles, like a heartbeat with an occasional irregular skip. This complexity rules out a simple, single rotating object. It suggests an interplay of multiple phenomena, a symphony of motions where shockwaves rebound off dense walls of gas, where jets precess, and where magnetic fields channel and focus energy in intricate, unpredictable ways. The nebula is not a static sculpture, it is a dynamic ecosystem, and its internal rhythms may be far more sophisticated than any simple model can capture. This leaves a tantalizing, albeit highly speculative, door slightly ajar. The precise and complex nature of some modulations has led a few researchers to wonder if we are seeing something entirely new. Could it be the signature of plasma instabilities on a scale we've never observed, where vast clouds of ionized gas oscillate in resonant harmony? Or does it point to the influence of previously undetected objects, like a binary star system whose orbital dance periodically focuses and deflects energy toward us? The Rosette Nebula's modulated whisper is a powerful reminder that even our best theories are still catching up to the universe's boundless creativity, challenging us to listen more carefully and imagine more boldly to decode the rhythms of creation itself. Leaving the familiar spiral arms of our own galaxy behind, we journey 160,000 light-years to a neighboring dwarf galaxy, the Large Magellanic Cloud, and into the heart of its most spectacular and terrifying stellar nursery, the Tarantula Nebula. Known officially as 30 Doradus, this region is the most active star-forming complex in our entire local group of galaxies. It's a cosmic cauldron of unbelievable proportions, a place where stars are born not in quiet isolation but in frantic, violent clusters. And the radio signals emanating from this extragalactic beast are just as extreme as its appearance, presenting a suite of anomalies that challenge the very foundations of what we thought we knew about how massive stars form. The first and most baffling characteristic of the tarantula's radio emissions is their sheer power and bizarre spectral shape. When we point our telescopes toward massive star-forming regions in our own galaxy, like the Carina Nebula, we receive a predictable combination of signals: the clear, sharp signature of hydrogen, the broader hum of heated dust, and the occasional intense spike from a water or methanol maser. The signals from the tarantula are different. They are dominated by a tremendously powerful, continuous broadband roar that swamps the more delicate spectral lines. It's as if the entire nebula is shouting, drowning out the individual voices of its constituent molecules. Embedded within this roar are maser signals, but they are orders of magnitude more powerful than any found in the Milky Way, and they flicker with a volatility that suggests an environment of unimaginable turbulence. This is where the mystery of distance adds a critical and confusing layer. Because the Tarantula Nebula is outside our galaxy, determining its exact distance is both crucial and notoriously difficult. Even a small error in that measurement can have huge implications for our interpretation of the signals. The power of a radio source follows what's known as the inverse square law. If you double the distance to a source, its observed strength drops by a factor of 4. So, if we have the distance wrong, our calculations of the energy required to produce these signals are completely off. Some measurements, particularly those using the subtle pulsations of variable stars within the nebula, have suggested the tarantula might be slightly further away than we once believed. If true, this would mean the nebula's internal engines are even more powerful than our already staggering estimates, forcing us to reconsider the upper limits of how energetic star formation can truly be. To truly grasp the tarantula's strangeness, we must compare it directly to its closest cousin within the Milky Way, the Cygnus X complex we discussed earlier. Both are immense, both are forming massive stars at a furious rate, and both produce a dominant broadband radio roar from synchrotron radiation. But the differences are what truly captivate astronomers. The broadband emission from Cygnus X, while powerful, still allows the distinct fingerprints of various molecules to be seen within it. In the tarantula, that broadband roar is so overwhelming it completely masks other features, suggesting a far greater density of relativistic electrons spiraling in magnetic fields. Furthermore, the masers in Cygnus X, though powerful, are relatively stable. The masers in the tarantula are chaotic giants, flaring and fading in ways that imply they are being pumped by an energy source far more violent and unstable than anything we see locally. This points toward a fundamental difference in the very nature of these stellar factories. Our galactic nurseries like Cygnus X are often built from multiple, separate clusters and clouds that have merged and interacted over time. The Tarantula Nebula, however, appears to be a single, monolithic starburst region. It's as if an entire giant molecular cloud decided to collapse and form stars all at once in one concentrated, catastrophic event. This creates a feedback loop of unbelievable intensity. The hottest, most massive stars blast out radiation and stellar winds that compress nearby gas, triggering more star formation, which in turn creates more massive stars in a runaway cycle of creation and destruction. The radio signals we detect are the integrated sound of this entire feedback engine operating at maximum volume, a collective shout from 100,000 stars being born and dying in a cosmic pressure cooker. The anomalies from the tarantula aren't just quirks, they are a message from an extreme regime of physics, showing us that the processes we study calmly in our own galactic backyard can explode into something truly monstrous on a different scale. Now we turn our gaze to a different kind of cosmic entity, one that is defined not by what it emits but by what it absorbs, a place of profound cosmic shadow known as the Coalsack Nebula. Lying just 600 light-years away in the constellation Crux, the Southern Cross, this is not a glowing cloud of ionized gas. It is a dark nebula, a cold, dense fortress of interstellar dust and molecular gas so thick it completely blocks the light from the millions of stars behind it, carving a void of blackness into the bright starfields of the Milky Way. For centuries, it was seen as little more than a hole in the sky. But when we listen to it with radio ears, we discover it is not silent at all. It is a place where signals don't just originate, they are absorbed, twisted, and transformed in deeply unusual ways, creating a unique and puzzling radio signature. The primary mystery of the Coalsack isn't a powerful burst or a strange emission. It is an absence, a profound and specific silence known as absorption. Radio telescopes pointed toward background sources like distant pulsars or quasars detect something strange as those signals pass through the nebula. At certain very specific frequencies, the signals are noticeably weakened, as if the cloud itself is swallowing them whole. This isn't random static, it's a targeted filtration. The frequencies being absorbed correspond to the predicted transitions of exotic molecules that can only form in the extreme cold and protection of such a dense cloud, things like carbon chain molecules and cyanopolline. The Coalsack acts as a cosmic spectrograph, its cold interior imprinting the unique, dark fingerprints of these complex molecules onto any signal that dares to pass through it. But the story is far more complex than a simple curtain of absorption. Some signals don't just get weaker, they change. Astronomers have detected anomalous scattering and Faraday rotation effects within the nebula. To visualize this, picture a clear, steady radio signal from a distant quasar as a straight, vibrating arrow flying toward Earth. As this arrow enters the Coalsack, it doesn't just get dimmer. The dense, magnetized plasma within the cloud causes the arrow to bend slightly and its polarization to slowly rotate, like a compass needle twisting as it passes over a powerful magnet. The signal that emerges from the other side of the nebula is subtly but definitively different from the signal that went in, carrying the unmistakable imprint of the cloud's internal structure, its magnetic field strength, and the turbulent motions of its hidden gas. This transformative power of the nebula leads to the most intriguing possibility of all, that the Coalsack is not merely a passive filter, but an active cloak hiding unknown sources within its dark embrace. Its incredible opacity at optical wavelengths means that entire star systems, Chinese letter, brown dwarfs or rogue planets, could be lurking deep inside, completely invisible to our optical telescopes. But at radio wavelengths, especially longer ones that can pierce the dust more effectively, we might be getting fleeting, distorted glimpses of these hidden objects. A weak, repeating radio burst from within the cloud could be the signature of a deeply embedded protostar with powerful magnetic flares. An unusual, narrow-band signal might be a maser, its emission scrambled and redirected by the complex maze of dust filaments it must navigate to escape. Advanced computer visualizations allow us to simulate this journey, to fly through the proposed structure of the Coalsack. We see the signal path not as a straight line, but as a twisting, turning corridor through a labyrinth of dark, dusty pillars. The signal bounces off dense walls of gas, is refracted around opaque knots of dust, and its strength is sapped as it collides with countless cold molecules. The visualization shows the signal's intensity fluctuating wildly along its path, and its polarization vector spinning erratically, a testament to the incredibly complex environment it is fighting through. What we receive at our telescopes is not a clean broadcast from a source, but a heavily edited and corrupted version of it, a message from the shadows that has been rewritten by the very cloud that hides its author. The Coalsack Nebula, therefore, stands as a cosmic puzzle box. Its mysteries are not written in light, but in the intricate ways it sculpts and shadows the radio waves that pass through it, challenging us to decode not just the signals of the universe, but the profound and complex silence in between. Moving upward through the constellation Cygnus, we find another celestial landmark, a cloud of gas and dust so vast and intricately shaped that it resembles a continent on Earth, the North America Nebula. Officially catalogued as NGC 7000, this magnificent emission nebula glows with the energetic light of newborn stars. It's a region we think we understand, a predictable stew of stellar winds and ionization. But when astronomers began a long-term study of its radio emissions, they detected a series of signals that behaved in a way that was anything but predictable. These were not static whistles or simple pulses. They were transmissions that seemed to slide gracefully up and down the radio dial, exhibiting a smooth, continuous change in frequency over time, a phenomenon known as frequency drift. In the cosmos, frequency drift is most often explained by the Doppler effect. It's the same principle that makes a passing ambulance's siren change pitch. If a source of radio waves is moving toward us, its waves get compressed, shifting the signal to a higher frequency, what we call a blue shift. If it's moving away, the waves are stretched, causing a red shift to a lower frequency. Within a turbulent nebula like NGC 7000, we expect to see this. Gas clouds orbit stars, jets of material shoot out at high speeds, and shockwaves expand. All of this motion should create a predictable, chaotic symphony of small Doppler shifts. But the signals from the North America Nebula are different. Their drifts are too smooth, too monotonic, and above all, they are in the wrong direction. Advanced computer visualizations help us see the problem clearly. One animation might show the complex internal dynamics of the nebula itself. We see vast streams of gas flowing in specific directions, propelled by stellar winds and gravitational pull. Arrows and color gradients map the expected velocity of the gas, and thus the predicted Doppler shifts for any signal originating within it. Then, superimposed over this animation, we see the actual path of one of these mysterious drifting signals. A bright line on a frequency versus time graph glides steadily upward, indicating a smooth, continuous blue shift. The problem is, the specific region of the nebula it's coming from is modeled to be moving almost directly away from us at that moment, which should produce a strong redshift. The signal is doing the exact opposite of what the physics of the cloud says it should. This contradiction forces astronomers to consider that the source of the signal might not be moving at all. Instead, the drift could be caused by something happening in the space between the source and our telescopes. One fascinating theory involves a phenomenon called plasma lensing. Imagine a small but dense, not of ionized gas, a plasma cloud drifting within the larger nebula. As this compact cloud moves through our line of sight, it passes between a steady background source of radio waves and Earth. The plasma within this cloud can act as a lens, but a very strange one. Unlike a glass lens that focuses light to a single point, a plasma lens is dispersive. Its focusing power changes dramatically with frequency. As the cloud moves, it would first focus the higher frequencies of the background signal toward us, causing a temporary brightening and a perceived blue shift. Then, as it continues its drift, it would focus the middle and finally the lower frequencies. To our instruments, this would appear not as a change in the source's velocity, but as a smooth, continuous drift of the entire signal from high frequency to low frequency, or vice versa, depending on the geometry. The drift we measure wouldn't be a real Doppler shift from motion. It would be an illusion, a chromatic mirage created by a natural lens made of magnetized gas moving through our field of view. This elegant explanation could account for the strange, smooth drifts, but it requires a precise and somewhat unlikely alignment of a small, dense plasma cloud and a steady background source. If this isn't the answer, we are left with even more exotic possibilities. Could the drift be intrinsic to the source itself? Perhaps we are witnessing a natural radio transmitter that is physically changing size, expanding or contracting in a way that systematically alters its broadcast frequency. Or could it be a signature of a processing jet, a beam of particles wobbling like a spinning top, its changing orientation sweeping a beam of radiation across space in a way that mimics a frequency drift? Each of these explanations points to a dynamic and poorly understood aspect of astrophysics, suggesting that within these beautiful, well-photographed nebulae, the fundamental interactions between matter, energy, and magnetic fields are still capable of producing profound and beautiful mysteries. But for all its explosive history, the veil holds a modern-day secret, a subtle anomaly in its radio song that has astronomers questioning if our understanding of cosmic explosions is truly complete. When we map the remnant's radio emissions in exquisite detail, we find something unexpected. The intensity of the signal isn't perfectly smooth or uniform. There are faint, patchy regions where the radio glow is just a little bit brighter or a little bit different than our standard models of shock acceleration predict. It's as if the fabric of the supernova remnant is woven with threads of a material we can't quite identify. Our standard model for a remnant like the veil is a masterpiece of energetic physics. We picture the outgoing blast wave a supersonic wall of energy and ejected material slammed into the cold, dormant interstellar medium. This collision is so violent it acts like a natural particle accelerator. Electrons get caught in the magnetic fields that are amplified and tangled by the shock itself, and as they spiral at nearly the speed of light, they emit synchrotron radiation, the radio waves we detect. Supercomputer simulations of this process are breathtaking. They show the shock front rippling and distorting as it plows through the gas, creating intricate filamentary structures that look almost identical to what we see in Hubble images. The simulations can even predict the rough brightness and spectrum of the radio emission, but they can't perfectly recreate those specific, subtle, bright spots we observe. There's a discrepancy, a faint excess of radio energy in certain areas that the models struggle to explain. This is where the mystery deepens and the speculation ventures into the realm of the exotic. One compelling theory suggests that the shock wave might be doing more than just accelerating electrons. It might be illuminating the invisible. What if the blast wave is plowing through a region of space that wasn't entirely empty? What if it was passing through a faint, diffuse clump of dark matter? If certain theoretical particles, like weakly interacting massive particles or WIMP, make up this dark matter, the incredible energy of the supernova shock could provide the catalyst for them to interact. If two of these particles were to collide and annihilate within the energized shock front, they would produce a secondary shower of standard particles, including electrons and positrons. This sudden injection of new, high-energy particles right at the shock would give the synchrotron radiation a localized boost, creating one of those strange, bright patches that doesn't fit the standard model. The Veil Nebula in this scenario becomes more than a fossil. It becomes a giant, natural particle detector, its radio glow potentially revealing the presence and properties of the universe's most elusive substance. Another fascinating possibility lies not with dark matter, but with the shock wave's interaction with pre-existing cosmic rays. The interstellar medium isn't a placid pool of neutral gas. It's already filled with a sea of high-energy particles, protons, and atomic nuclei that are constantly zipping through space. As the veil's shock wave expands, it doesn't just accelerate fresh electrons from the gas. it can also re-accelerate this existing population of cosmic rays. The physics of this process, known as re-acceleration, is incredibly complex and is highly sensitive to the shock's precise speed, strength, and the magnetic environment around it. The unusual emissions could be the signature of this secondary acceleration mechanism, a subtle effect that our current simulations are only beginning to incorporate. The Veil nebula's puzzle, therefore, might not point to new physics, but to a more nuanced understanding of old physics, revealing the intricate and layered ways a supernova remnant interacts with its environment long after the initial fireball has faded. Yet even the explosive history of a supernova cannot compare to the profound silence of a dark nebula, a place where creation is not marked by brilliant light, but by the subtle stirrings of chemistry in the cold and the dark. And few dark nebulae are more iconic, more instantly recognizable than the Horsehead Nebula in Orion. This magnificent pillar of cosmic dust, sculpted by stellar winds into the shape of a stallion's head, is a silhouette against the glowing pink hydrogen gas of the larger IC 434 region. For over a century, it has been a favorite target for astrophotographers, a beautiful monument in the sky. But when we shift our view from the optical to the radio spectrum, this silent sentinel begins to whisper, revealing a mystery unfolding within its inky shadows. The signals emanating from the heart of the Horsehead are not the brilliant shouts of a maser or the explosive burst of a transient event. They are incredibly faint, a persistent, whispering static that requires our most sensitive radio telescopes, tuned to very specific frequencies, to even detect. Their spectral signature is what makes them so unusual. They don't appear as the clean, sharp spikes we associate with simple molecules like carbon monoxide. Instead, they manifest as a complex series of broad, smeared-out humps and bumps spread across a range of frequencies. It's not the clear note of a single instrument, but the blended, muddy chord of an entire orchestra playing just on the edge of hearing, with many of the instruments being ones we don't yet recognize. To understand the potential source of these whispers, we must venture in our minds deep into the freezing heart of the nebula itself. The environment here is extreme, but in a way completely opposite to the violence of the Veil. Temperatures hover just a few degrees above absolute zero. The density of the gas and dust is so high that it blocks virtually all external starlight, creating a deep cosmic freezer that is, paradoxically, a perfect nursery for complex chemistry. Here, simple atoms and molecules like carbon, oxygen, and hydrogen don't just float freely. They slowly drift until they stick to the surface of microscopic, icy dust grains. These grains act as tiny chemical laboratories, providing a solid stage where these basic ingredients can meet, link up, and form increasingly complex molecular structures. Animating this process reveals a beautiful and intricate dance. We can visualize a carbon atom drifting through the void until it adheres to a dust grain, a tiny speck of ice and silicate. An oxygen atom soon follows, bonding with the carbon. Then a hydrogen atom attaches, forming a simple formaldehyde molecule. Over eons, more atoms arrive, building up longer and longer carbon chains, creating molecules known as polyines or cyanopolymers. Some of these molecules can grow to impressive sizes, becoming tiny, branched hydrocarbons or even the precursors to amino acids, the building blocks of life. These are not the hard, rigid structures we picture in textbooks. In the cold of space, they are flexible, vibrating, and rotating constantly, and it is this movement that holds the key to the whispers. Each time one of these complex molecules rotates or vibrates, it can emit or absorb a photon of radio wave energy at a very specific frequency. The larger and more complex the molecule, the more ways it can twist and turn, leading to a far more complex spectrum of emission, a dense, overlapping forest of faint spectral lines rather than a few clean, isolated trees. The broad, blended signals we detect from the Horsehead could very well be the collective, faint hum of billions upon billions of these large organic molecules tumbling in the dark, their individual voices blending into a continuous whispering chorus. However, the extreme conditions within the nebula also compel scientists to consider even more exotic possibilities. Could these signals be the signature of unknown physical processes unique to such high-density, ultra-cold environments? One theory involves quantum tunneling effects on a macroscopic scale. In the profound cold, the usual rules of chemical reactions can break down. Reactions that would require significant heat to proceed on Earth can instead happen through quantum mechanical tunneling, where particles simply appear on the other side of an energy barrier. This could facilitate the formation of strange, metastable molecules that cannot exist anywhere else, and whose rotational spectra would be entirely new to science. Another speculative idea points to the interaction of cosmic rays with the dense ice mantles on the dust grains. When a high-energy cosmic ray pierces a grain, it could deposit energy that triggers a localized burst of complex chemistry, or even create a temporary, localized plasma that emits its own unique radio fingerprint. The persistent whispers from the Horsehead Nebula are a haunting reminder that some of the universe's most profound secrets are not shouted from the rooftops of brilliant stars, but murmured in the deepest, darkest corners of cold cosmic clouds, where the ingredients of life itself are slowly, silently being assembled. Descending into the heart of the Orion Nebula, we find the Trapezium Cluster, a group of brilliant, massive young stars that act as the powerful engine lighting up the entire stellar nursery. It's here, in this chaotic and radiant environment, that our most sensitive instruments have detected signals so bizarre they seem to defy categorization. These aren't pure tones or simple pulses. They are intricate layered composites, a chaotic symphony where the shrill whistle of a thermal emission overlaps with the deep roar of synchrotron radiation, all woven together with the sharp, narrow spike of a maser. It's as if the universe's radio orchestra decided to play every single movement of its symphony at the exact same time, creating a signal of breathtaking complexity that we are only just beginning to untangle. To understand why this is so unusual, imagine trying to identify an animal by its sound. Most cosmic signals are distinct: the rhythmic chirp of a pulsar, the steady hiss of hot gas, or the pure tone of a maser. The composite signals from the trapezium are like hearing the roar of a lion, the chirp of a cricket, and the rumble of an earthquake simultaneously from the same tiny point in space. This suggests an environment where multiple, wildly different physical processes are occurring not just nearby, but are intrinsically linked, perhaps even feeding off one another in a self-sustaining loop of cosmic energy. The very existence of such a combined signal hints at astrophysical phenomena we have yet to discover or fully understand. The true power of this investigation is revealed through multi-wavelength data visualizations. A standard optical image of the trapezium shows the four bright stars and the glowing gas they illuminate. But when we layer on data from different parts of the electromagnetic spectrum, the scene transforms into a multi-dimensional masterpiece. In these composite visualizations, the infrared data from the James Webb Space Telescope unveils hundreds of hidden protostars still embedded in their dusty cocoons. The X-ray data from the Chandra Observatory reveals incredibly hot, million-degree gas from violent stellar flares. And then, laid over it all, the radio data paints the final, crucial piece. Not a smooth glow, but a complex, intricate web of these composite signals, each one a tangled knot of emission that appears to be anchored at the nexus of multiple energetic events. One compelling theory for these hybrid signals involves the concept of a cosmic particle accelerator operating on a staggering scale. The fierce stellar winds from the trapezium stars are constantly colliding, creating immense, standing shock fronts that ripple through the surrounding gas. These shocks are natural accelerators capable of driving electrons to nearly the speed of light. Now, imagine one of these supercharged electrons screaming through the nebula. It could first produce synchrotron radiation, that broad, roaring base of the signal, as it spirals along a magnetic field line. A millisecond later, that same electron might slam into a dense knot of cold molecular gas, heating it rapidly and generating a burst of thermal radiation, the sharp, hissing component. And if that knot of gas is rich in water or methanol molecules, the sudden injection of energy could pump them up, triggering a maser emission, the final, pure-toned spike on top. One single event, one single particle, could be the catalyst for all three components of the signal simultaneously. Another, even more dynamic possibility involves the very geometry of the region. The environment around the trapezium is not static. It is a constantly shifting labyrinth of gas pillars, protoplanetary disks, and streaming jets of material. A composite signal might originate from a location where the jet from a newborn star is actively plowing into the dense wall of a nearby protoplanetary disk belonging to another star. The impact site would be a maelstrom of competing physics. The jet itself generates synchrotron radiation, the shocked and compressed disk material radiates thermally, and the interface where the two meet could be a perfect factory for maser action. We would be witnessing, in a single radio signature, the violent interaction between two infant solar systems, a dramatic snapshot of the chaotic processes that govern the birth of stars and planets. The presence of these unexplained composite signals challenges us to rethink the very boundaries we draw between different astrophysical phenomena. They suggest that in the most extreme environments, these processes are not separate at all, but are parts of a single, interconnected system, a continuum of energy conversion that we are only now learning to observe as a whole. Each complex signal from Orion's sword is a unique key, a cipher that, once decoded, could unlock a new understanding of how feedback works in stellar nurseries, how particles are accelerated to incredible energies, and how the fierce light of newborn stars shapes the chaotic, beautiful, and infinitely complex clouds from which they themselves were born. From the startling brevity of the wow signal to the harmonic chords echoing from the Omega Nebula, each of these 25 unexplained transmissions represents a frontier of our understanding. They are not merely anomalies to be catalogued and forgotten. They are the very questions that will define the next chapter of astronomy. The Lorimer burst ripped open an entirely new field of study with its 5 milliseconds of power, while the persistent whispers from dark clouds like the coal sack and the horsehead hint at a universe rich with complex chemistry we are only beginning to imagine. The perfect harmonics of Messier 17 and the polarized scream from the Eagle Nebula's pillars show us that nature is a master of ordered complexity, capable of creating signals that mock our hopes of finding simple answers. And the drifting frequencies from the North America Nebula and the transient flashes in the lagoon remind us that the medium itself is an active player, a cosmic illusionist that can bend, amplify, and distort reality on a scale we are still struggling to comprehend. Collectively, these mysteries force a profound shift in how we view the search for extraterrestrial intelligence. They are a masterclass in cosmic humility, teaching us that the universe is capable of generating phenomena that are, for all intents and purposes, indistinguishable from technology. A signal can be narrow-band, polarized, and drifting, checking every box on our wish list, and still be the product of a swirling gas cloud acting as a natural lens for a distant quasar. This doesn't make the search futile, it makes it more rigorous. It pushes us to demand more from a potential discovery, to search for signals that are not just orderly, but information-rich, carrying the complex patterns that nature, for all its engineering genius, seems unlikely to produce by accident. The true lesson is that the greatest discovery might not be a message, but a deeper understanding of the natural universe's astonishing ability to mimic one. This journey through the whispers and shouts of the cosmos is far from over. Every new telescope, every advanced algorithm, brings us closer to unraveling these enigmas, and undoubtedly to discovering new ones that will challenge our theories all over again. The universe is not silent, it is a symphony, and we are only just learning to hear its most incredible movements. Now we want to hear from you. Which of these 25 signals captured your imagination the most? Was it the tantalizing, almost message of BLC-1 from Proxima Centauri, the explosive mystery of the first fast radio burst, or the harmonic beauty of a nebula singing in perfect mathematical harmony? Let us know in the comments below which cosmic mystery you find most compelling and why. If you enjoyed this deep dive into the unknown, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the greatest space mystery.